Now, stream function is the new topic that I would like to cover. So in order to understand the stream function, first consider the concept of streamline. As all you know that the fluid particle follows a path whenever they flow. So for example, if it is a fluid particle that I am considering, it is the path line, and this will become streamlined when the velocity vector will become tangent on it. So for a streamline, the velocity vector has to be tangent onto the line of flow of fluid particle. Now subsequently, I would like to consider multiple streamlines and flow between them such that I will define my stream function. Now I would like to derive the equation for my stream function. So a stream function is a scalar function whose derivative determines the velocity vector uniquely. So in order to define this relation, consider, for example, two streamline defined by this psi 1 and psi 2, my two streamlines, and the fluid is flowing between these two streamlines with a velocity v. This is the flow direction, and this is the direction of the normal to the velocity field, and that normal subsequently can be resolved into two components, which is my del y and this is my del x. So this normal is like the area, so it has two components, del x and del y. So as I mentioned, the flow between two streamlines psi 1 and psi 2 is defined by this geometry. So once I have that, I can easily write the formula for volumetric flow rate, which is velocity multiplied by the normal area. So this is my volumetric flow rate mathematically, or it can also be written in terms of components as u del y minus v del x. Now subsequently, to satisfy the flow continuity, I can also write down the volumetric flow rate in terms of the components of velocities, that is fluid coming out from the normal and fluid coming out from the horizontal surface of that element. Also, the difference of streamline will provide the volumetric flow rate. This is definition. So it means that mathematically I can write down psi 2 minus psi 1 equal to v into the area into which fluid is entering, which is my volumetric flow rate. So subsequently, if del n multiplied by the velocity is volumetric flow rate, and subsequently it has been equated and substituted for this value which we already have determined, so I can write down del psi as this equation. Now for my limit, when this area del n is becoming smaller, then I can write down this in terms of the derivative, ordinary total derivative. Now on the other hand, if I consider my psi function, which is a scalar function, and it depends on two parameters x and y, so I can easily write down this relation based on the definition of my total derivative, total change. So it should be like that. Now I have two different equations, so I will go and make the comparison of these two equations to extract the values of u and v. Now upon comparing the two equations, I have obtained these relations for my u and v. So the good thing here is that a scalar function psi can exist for a typical flow field. There are some conditions that have to satisfy, and once I have that stream function, I can easily determine the corresponding velocity distribution for that particular flow field. Now these two equations automatically satisfy the continuity condition. So it means that a stream function automatically satisfies the continuity condition. And here you have seen that I have substituted the velocity components in the continuity equation and check that, and it has been satisfied. So next I would like to mention some conditions that you have to satisfy in order to check the existence of a stream function. So in addition to the previous condition of continuity, there exists some other condition also that you must check for the existence of a stream function. So first condition is steady or unsteady incompressible flow. That if you have an incompressible flow field where the density is constant, so a flow either if steady or unsteady, you can define a stream function for that. Now we can also define a stream function for a compressible flow where the density is variable, but make sure the flow is steady. Another important thing is the stream function is limited to a 2D flow field or a axisymmetric flow field. So a stream function allow us working with a scalar function instead of a velocity vector. That is, by defining a stream function for a particular flow field, we can easily calculate the velocity component and subsequently can perform the flow analysis. So flow analysis means I can easily calculate the pressure distribution, the volumetric flow rate, and etc. The third point I would like to describe for an irrotational flow field, and the condition for irrotational flow is the vorticity should be 0, and for a 2D case I have written down this equation, which is subsequently written in this form. So in this equation I will go and substitute the values of u and v component in terms of a stream function and will check the equation. So here is another mathematical identity that I have obtained after substituting the components of velocity in the vorticity equation. So this equation is commonly known as Laplace equation, which has been defined for a incompressible and irrotational flow. So we have another scalar function known as potential function. So for an irrotational flow, we can define a scalar function whose gradient is v. So that scalar function is indicated by this symbol phi or phi, and mathematically we can define this as so the gradient of that scalar function, the potential function, will provide the velocity vector. Subsequently, from potential function I can derive the velocity potential equation. However, I have to impose another condition, which is for an incompressible flow. So for incompressible flow, we know that del dot v should be equal to 0. So after substituting the value of V here, I obtain this equation by performing the dot product between two del operators. So this equation is again my Laplace equation and commonly known as a velocity potential equation for an incompressible flow. This is a second order linear partial differential equation and it is classified as an elliptic equation. So this equation can be represented in both Cartesian and cylindrical coordinate, which you will see in the next slide. Here the equation has been represented in Cartesian as well as cylindrical coordinates, and this is a linear equation. Various solutions may exist. Mathematically there will be n number of solutions. So since the equation is linear, so the solution can be combined. For example, phi1 and phi2 are two different solutions. They can be combined to get the other solution. So in summary, I will say that for my irrotational flow, del cross V should be 0. This implies that my phi will exist. And once your phi exists, then velocity can be obtained through this. And when I go and impose the irrotational and incompressible flow condition, then I will obtain my velocity potential equation.